Yep, it's good.
Great. And if
Very
others could mute while we're presenting, I appreciate that. And I'll put your questions in the chat box and then we'll go through them at the end. Wanted to start off, though, briefly, just to thank Krishna for his leadership. He started this webinar series, at a time when the world was really in a tumultuous state with COVID, and this brought a lot of people together all around the world, and had the foresight to do that and the insight to continue it afterwards as a way of continuing to bond our community together. I think he deserves a lot of credit for that insight and leadership, and so thank you, Krishna. I presented last summer in 2021, I believe in August, on a related topic, on a discussion of a study we had done with Nuclear Regulatory Commission and the U.S. Department of Energy, exploring the in-service condition of historical uranium mill tailings disposal facilities that have been constructed 30 years ago. And we talked about how they had altered over time. And today's study has some commonalities with that, because it also deals with uranium mill tailings disposal facilities, and particularly how their final covers function, with a specific focus on the type of cover and the way we go about managing it. And we're particularly going to talk about an idea called naturalization, where instead of managing the cover deliberately, we essentially build a cover and let nature essentially take hold of that cover and turn it into her own, and use that, harness nature's processes to our benefit in terms of containment. And you'll see that as we go through. Before I kind of dig into it, I'm going to share work that a lot of us have collaborated on. The work has been sponsored by U.S. Department of Energy, both legacy management of DOE manages sites after they've been built and closed. So build a uranium mill tailings disposal facility. Ultimately, it becomes the Department of Energy legacy management's responsibility. Department of Energy environmental management is responsible for environmental restoration of the broader environment associated with the weapons complex in the United States. And just a bit of information, in the United States, that's our third largest financial liability for the federal government, behind Social Security, which is our national retirement program, Medicare, our national health care program for retirees, and then it's cleanup from the Cold War. So these agencies have a big responsibility. And DOE EM sponsors our CRESP consortium, which is a multi-university consortium that does applied and translational research to help them efficiently and confidently go about their mission in terms of environmental cleanup. The number of people I've worked with throughout the years on this that participated really intimately with this: Bill Albright, who's a research hydrologist emeritus at Desert Research Institute. Bill and I have worked together for 25 years. Jody Waugh, who's a ecologist emeritus from DOE Legacy Management. A lot of emeritus. We all have gray hair these days. Preacha Apawantragoon, who's one of my former PhD students, who still does a lot of the water balance work for us. He's a colonel in the Royal Thai military, and a faculty member at the Royal Military Academy. And then two other folks, Aaron Tiger and David Holbrook, some younger scientists who work with DOE LM, who are very much engaged in these projects on a day-to-day basis. So while I'm talking today, all those people contributed both with their labor and their intellectual contributions as well. All of you, maybe not all of you, are familiar with what uranium mill tailings are. It's a byproduct of processing uranium. And I thought we'd just take a moment to describe what it is, so you get a sense of the context of, one, where it comes from, but how much of it we have to manage. We start with uranium ore, which is a rock. I think the most common name for it is pitch blende. has less than 1% uranium in it. We take that rock, we take it out of the ground, we take it to a mill where we grind it into a very fine silt-sized material, and then we take that very finely ground material and immerse it in a chemical solution that extracts the uranium. And from that, we'll create something called yellow cake. And yellow cake is what ultimately becomes, for example, a fuel rod down the road. It would be processed more to become a fuel rod for a nuclear reactor to generate electricity. That uranium that's in the ore is less than 1% by mass. So think of when we're running a uranium mill, that means 99% of the rock that we've ground up and immersed in a chemical solution is waste product. And that's uranium mill tailings. Tailings is the byproduct, the tail end of the refining process. And they're typically disposed in very large ponds. And that's what I showed down here in the lower right-hand corner. That's a uranium mill tailings disposal facility. And they can be hundreds of acres in size, very large facilities. And during the end of World War II and then the Cold War in the 1960s and 70s, and also the evolution of nuclear power in the United States and around the world, there was a huge growth in the mining of uranium and the refining of uranium mill tailing, uranium ore to create uranium fuel rods and other materials, but also producing enormous amounts of uranium mill tailings that needed to be processed. And at the time, in the 60s and early 70s, we really had no rules on how this was done. And a lot of it was done, you put the tailings out the back of the mill and there they lay. And they had impacts on the environment as a consequence. In the 1970s, a whole series of regulations were passed in terms of environmental change in the United States. First, the EPA was formed by President Nixon, and then the Resource Conservation and Recovery Act in 1976. And in 1978, US EPA was authorized through the Uranium Mill Tailings Radiation and Control Act, or UMTRCA, to develop standards for disposal of uranium mill waste and to remediate the existing mills that were on site or throughout the nation that had mill tailings disposal problems at their facilities. And just to give you a sense of the volume, 40 million cubic meters of low-level radioactive material was being moved as part of UMTRCA from uncontrolled disposal facilities into disposal facilities. So that's kind of the historic context of where UMTRCA came from and why it was created, to take this radioactive byproduct, a chemical byproduct of liquid and solid, radioactive, and also a whole series of other chemicals that was essentially released into the environment uncontrolled, and to put it in a controlled setting where we could monitor it, that it wasn't impacting the environment in a negative way. And the basis of a uranium mill tailings disposal facility is it's actually very simple. These are typically our unlined disposal facilities, essentially a landfill, where we place the uranium mill tailings. They will often be placed in a somewhat dewatered state, but they're often unlined. So it's an unlined disposal facility. And when final grades are reached, a cover system is built on the top. A little different than what we might use for example, municipal solid waste or hazardous waste, where we'd have a liner in the bottom and a cover on the top, leachate collection system on the interior. The philosophy at the time for uranium mill tailings disposal facilities was that the cap was the final line of defense, and specifically not putting a liner in the facility with the idea of minimizing the potential for long-term accumulation of water within the mill tailings that might then leach out contaminants and ultimately become a radioactive flux to groundwater. The idea was to minimize that potential for pooling. The cover, therefore, has a critically important role. It is the mechanism by which we control the movement of liquid fluxes and gaseous fluxes through the system. We're trying to minimize water percolation rates and also minimize gaseous emissions of radon. As the radionuclides within uranium mill tailings degrade, they generate radon gas. That radon gas moves up to the atmosphere and out of the facility, just like water would move down and into the facility. So the cover is actually functioning in two roles: gas control up and water control downward. And so the cover is just critically important. It is the barrier that protects the environment, both for long-term water percolation control, because what goes through the cover ultimately goes through the tailings and becomes the flux to groundwater. So that cover has to be very tight in terms of its water transmission capabilities, and also be able to manage radon flux. And if you were present in my seminar in August of 21, we talked about the radon fluxes and actually how these facilities, even being 3 decades old in some cases, are very effective in controlling those fluxes. The strategy that came out of the UMTRC regulations, and then through a series of activities with Department of Energy, was to develop a multi-layer cover on the top. One aspect I didn't mention in my previous slide, and I should have, and it's an important part of this, is that not only did the cover have to function, but it has to function for at least 1,000 years. There aren't many things in our environment that engineers have created that actually function for 100 years. But now we have to design something that's going to function for 1,000 years with very low percolation rates. And the thinking was at the time twofold. One, that we could put a barrier at depth that would both control gas emission up and water flow down. That was the radon barrier, a low conductivity radon barrier, a compacted clay barrier at depth that was built with very fine pores, high water saturation, so it has low gaseous diffusion to radon and low hydraulic conductivity to water that would generate percolation. To have this radon barrier at depth, then to protect it from freezing with a frost protection layer, it's about 600 millimeters thick, and then to protect the frost protection and radon barrier from what was considered at the time perhaps the most significant factor affecting long-term performance, which was erosion. But a very robust erosion control system at the top. This system was also managed as well. Any vegetation that was might develop on the surface was removed through herbicide. So you can imagine the operations and maintenance challenge with this as well. You've got a remote disposal facility that you have to continuously visit and determine whether it's got any vegetation that's started to establish on the site, and spray it with herbicide to prevent that herbicide from essentially developing a vegetative community on the site. The vegetation control was done for 2 reasons. One, concern about radionuclide uptake. So if the vegetation would root down through the cover and ultimately into the tailings below, it could become a source for radionuclide uptake that might ultimately be into the biomass on the surface and then get transported through either animals eating the vegetation or through die-off of the vegetation and wind-blown organic matter being distributed. The other thinking with the vegetation as well was to prevent deep root intrusion that might develop structure within the radon barrier. So the idea was that if I put a frost protection layer on and I put a bedding layer and a riprap cover on top, I was going to protect that radon barrier, and it would remain effective in terms of controlling gas and controlling water flow essentially forever. Now that was the principle, not necessarily the reality. But that was the philosophy. I think one of the things that we've learned over the last 30 years about containment system is that we build a containment system, and nature looks at that containment system we built, and the more that containment system differs from its natural surroundings, the more quickly nature will begin to degrade the system. To put that in context, I like to show this photograph. This is the Blue Water, New Mexico uranium mill tailings disposal facility. Just get a sense for this. This is if you could mute in the background, that would be great. So we have a very large disposal facility, 1,300 hectares, 16 million cubic meters in this cell alone. Enormous disposal facility, all covered with rock. Now think about that facility and look at the surroundings. Does anything in the surroundings look like that facility? And I think the answer to that, if you just look at the photograph, is no. And so we've created something that our engineering, from our engineering perspective, is going to be highly resistant to the failure modes we're considering, but we're also putting something that's contrasts the natural environment in a very substantial way. And you can imagine that nature looks at that disposal facility and says, that doesn't fit here. I'm going to begin to alter that disposal facility so that it fits into the surroundings. And that's what we see. And we talked about some of that last summer as well. And this particular disposal facility, this is an early one that had a radon barrier at depth about 0.9 meters, and then no frost protection layer. Those came a little later. And then the bedding layer and the riprap layer. So this is an older one without that frost protection layer. I should state that we know that the barrier layer in this system has become very permeable, but the radon gas control remains very effective. And we talked about that last year. So then we had a design that was put in with the intention of functioning for 1,000 years with this barrier layer at depth. But what we've learned over time is that barrier layers that we put at depth are, particularly clay barriers that are near the surface, are unusual in the environment. The natural environment doesn't have low conductivity clay barriers within a couple of meters of the surface. They just don't exist. And what nature does is takes a barrier that we very carefully engineer and place in the subsurface, in a cap, for example, and alters it over time. And it develops structure. So we build it, we compact it, we place that material in a way so it has very fine pores with very low hydraulic conductivity, very low gas diffusion coefficient, and nature changes it. It develops structure in that system like I show here in this photograph on the left. And then over here, actually, it's a field photograph from a site out in California that we were monitoring. And actually, you can see a root intruding right down through that crack in the barrier layer. So nature takes our systems and alters them to make them congruent with her surroundings. And we've found over time in other studies that we've done, if we look at the hydraulic conductivity of barrier layers, like those used in UMTRCA facilities, that they tend to become altered substantially over time. And that's what I show you over here with this graph on the left. This graph is from a series of exhumations of facilities that we did in the last decade, where we compared as-built saturated conductivity of barrier layers in final covers, and then went back years later and measured their in-surface saturated hydraulic conductivity. And if there was no change in that system, we would expect the in-service to be very similar to the as-built, and data would fall along this green band. And in fact, we look at that graph and we don't see any data falling along that green band. We see all of the data falling up in this yellow band, this horizontal band. And for whatever reason, nature takes barriers, alters them, develops structure, and they ultimately have a hydraulic conductivity between about 10 to the minus 7 and 10 to the minus 5 meters per second. Why it's that range, I don't know. I think it has to do with some optimization in the natural ecological environment and how it interacts with the hydrology. Why it's that band, we don't know, but we do know no matter where we put our barrier layer in, that's where nature is going to take it. And we've seen that, as I mentioned, in our exhumation study. And then last summer, I talked about our study of radon barriers in particular, these historical ones where we went back and exhumed them. These are a couple different examples from that, the Falls City site in Texas and the Blue Water, New Mexico site I showed in a photograph just a few moments ago. And these sites were designed to have radon barriers that had saturated conductivity in the range shown by these yellow bands, less than 10 to the minus 9 meters per second. 20, 30 years later, we see something very different. Everything's moved over into that green band, which is directly analogous to what I showed in the previous slide. And in fact, at those sites, we looked at analogs, nearby analogs, and found that the analog profiles in the natural environment had similar hydraulic conductivities as well. So nature is manipulating these systems. We engineer them with an intent on having them perform a certain way for 1,000 years, and we build it, and then nature begins to alter the system to make it more congruent with the surroundings. Just another example of this, and some of the mechanisms that cause this. This is a radon barrier from Monticello, Utah. This is, if you've been to Utah in the United States, it's in the southwest United States, and this particular site is on the eastern edge, southeastern edge of Utah. A beautiful location right near the Big Ears National Monument. But there's a uranium mill tailings disposal facility there and a series of test caissons that we exhumed to look at the condition of radon barriers at depth years after they had been placed. And this radon barrier here is between 1.6 and 1.9 meters deep, very deep below the ground surface. And this was placed to be a very wet, soft, low conductivity radon barrier. And what do we see? 15 years later, when we look at this photograph, we see what looks like a dry, hard section of radon barrier. We've exhumed down to this point in the barrier. We see lots of cracks here. We see where the barrier is actually pulled apart at this interface when we've gone down and excavated it. We see plant roots in that interface. Plants are extending their roots down regardless of our efforts to prevent that, and extracting the water from the radon barrier because it has available water. We put it in wet. A plant sees that water as a resource and extends roots down to that barrier and pulls that water back out. So you can see that all the effort that went in to build this very, very low conductivity radon barrier was largely moot, at least from a hydraulic control perspective. Interestingly enough, you can see at the bottom here where this barrier was built in lifts and how the lifts actually have pulled apart right here at these surfaces below. So that's what we see. In 2007, when we were beginning to work on a lot of these activities and learning about how they how systems were behaving over time, and doing some of these exhumations and finding that some of the barriers were more permeable than expected, we had an opportunity to build a test facility for the Department of Energy to evaluate at near full scale the conventional radon barrier design that had been constructed at numerous sites throughout the United States. The typical design I showed earlier. This is the Grand Junction test facility in Grand Junction, Colorado. This is west of the Rockies. So you imagine if you're in Denver, go west about 3 hours, go over the Rocky Mountains, and you'll be in Grand Junction. This test facility that we developed for DOE had a couple of objectives. One objective was to evaluate actually how are these covers functioning hydraulically. Are we actually controlling percolation to the degree that we expected? And if you remember on a slide, several slides back, I talked about the goal was to get the percolation rate on the order of 3 millimeters per year. So a very minute amount of liquid draining from the base of the cover and into the tailings. Was that actually being realized? Many of these were built, but actually nobody actually ever measured whether they were functioning properly. So one objective of this facility was to evaluate whether we were achieving our goals. Another objective was to think about how we managed it. Because as I mentioned, these facilities, we have this rock surface cover on the surface, and that actually becomes a home to vegetation over time. And the management strategy is to very deliberately to spray that any vegetation that emerges on that system and eliminate the presence of any vegetation on the surface. Is that important to do? And maybe rather than going to all this effort to prevent the ingress of nature and the presence of vegetation, maybe we ought to just let it sit. What would happen if we stopped managing it and just observed how it functioned over time and let nature begin to manage the hydrology as opposed to man? So we built test sections that represented that profile that I showed earlier. We built these in a so-called Acap Drainage Lysimeter. Acap was the alternative cover assessment program that we ran for US EPA in the 1990s and the first decade of the 2000s. These were essentially large bathtubs. There's a large bathtub built out of a geomembrane in which we would build the cover profile inside. And at the bottom of that bathtub was a drainage layer in which we would collect any liquid which would drain out the bottom, and we would route it to a sump and then out to a percolation monitoring basin, as I'll show in some photographs in a bit. We would also measure any surface flow at the surface, and in some cases, at some sites where we had internal lateral flow, we might have some other takeouts as well. For these facilities, we didn't. We measured lateral flow at the surface, so this would be flow right at the bottom of the riprap bedding layer and at the top of the protection layer. These facilities really don't have runoff because they're so coarse at the surface. All the water that reaches the surface from precipitation ultimately goes down through that riprap layer and then starts to move laterally once it hits the finer textured protective layer at depth. But we built these big bathtubs, and I'll show some photographs of these in a minute. Monitored all components of the water balance. We also monitored the state within the system with measuring water content, temperature, matrix potential as a function of depth and location over time. And that allowed us essentially to characterize all components of the water balance. We built two of these side by side, so we had replicate tests. These were built in a large test facility. I'll show a photograph of this in a minute, right next to the Grand Junction disposal facility, which manages uranium mill tailings and other low-level radioactive waste generated as part of decommissioning activities for the US Department of Energy. For 7 years, we ran the duplicate tests out in the environment and monitored how they would function. Nobody had done that before. We were understanding how these systems, which we had built dozens of throughout the United States, how well they would actually function hydrologically. After 7 years, we took one of these sections and stopped managing it the way that's conventionally done. And I should mention, when both test facilities, we built them and we operated them just like you would a conventional uranium mill tailings disposal facility. That included regularly visiting the site, inspecting it for vegetation, and removing that vegetation if it was present. After 7 years, the one test section, which I call naturalized here, we stopped spraying the vegetation. We stopped managing it. We just let nature manage the cover system as opposed to mankind. Here's some photographs that I said I would show. This is gives you a sense for scale. You can see the Rocky Mountains in the background. You get a sense for this climate. It's semi-arid. Here we're building the foundation for our test facility. It gives you a sense for the scale of this project. We built the lysimeters that I talked about, putting them in place with conventional geomembrane installation. These were all the welds were tested with conventional techniques. We also filled our lysimeters with water and made sure they were leak tight before we completed them. On top of the geomembrane, we had a geocomposite drain that I mentioned. That's at the bottom that allows liquid to be conveyed to the sump. And then we began to fill it. This is the bottom of it. This is the transition layer at the bottom, shown in some of the earlier profiles. And early on in it, bring that fill in on the inside. And then you can see here on the right, we're folding up the sidewalls of the lysimeter as we go. And you can see what a great place to do field work. We get the Rocky Mountains in the background, just fantastic. And in the very background here is the Grand Junction disposal facility. So we're right next to an operating uranium mill tailings disposal facility. A couple more photographs illustrating how this works. On the left here, we see the transition layers being placed, and we're getting ready to bring in the radon barrier into our box, all right, into our bathtub. Over here, we've constructed the radon barrier. This was built using the exact same specifications employed for the radon barrier in the disposal facility you can see in the background. So the radon barrier in this facility, we use those specs to build this radon barrier here. And after we installed the radon barrier, built it, we collected large block samples out of it for hydraulic properties characterization, these large undisturbed samples. And finished the construction and brought it up. And this is what it looks like at completion. You can see the two lysimeters. Here's the one on the left. This was the conventional. And then on the right, the naturalized. You get a sense for scale with the loader down here in the front. You can see, again, the beautiful Rocky Mountains in the background. We've got some pipes showing in here. This is instrumentation conduit where all of the wires were coming from our test sections to monitor state variables. And if we look closely, there's a couple of look like green drums at the Toa slope here at the front of both test sections. And that's a monitoring basin. I mentioned liquid be conveyed into the sumps through a pipe and then to a monitoring point. And that's what these look like. These are large, essentially big pipes built in the ground or a caisson of sorts. Inside those, we had a series of systems that would allow us to meter the flows with a high degree of precision. We had triple redundancy in monitoring flows, and we could measure the percolation rate with an accuracy of 1/10 of a millimeter per year per unit area. So highly accurate system to measure the percolation rate. Couple that with on-site meteorological instrumentation. So we're measuring meteorological conditions right on the surface, and instrumentation installed within the cover profile, like the CS616 water content reflectometers, TDR method to measure water content. So a full suite of instrumentation that allowed us to have complete detailed understanding of the water balance at the site. You get a sense for the robustness of that surface layer as well. This is the cobble that's used, cobble riprap used for erosion control at the surface, right in the foreground. This is large, rounded, hard rock that's meant to last for a very, very long time. Okay, well, how did it work? What did we find? Well, remember, we're thinking that this will be about 3 millimeters per year of percolation. And not only in the first year, but 1,000 years, all right? Here's our two test sections. These are water balance graphs. They have time on the x-axis, and on the y-axis, they have different water balance quantities. So cumulative precipitation that's falling on the site, evapotranspiration, what's being transmitted back to the atmosphere, percolation, what's coming out the bottom of the cover, lateral flow, that's like runoff, but recognizing it's at the interface of the bedding layer and the protective layer because that cobble allows everything to enter at the surface. And then soil water storage, which is just the total amount of water stored within the cover profile over time. And I have one of these graphs for conventional and then one for the so-called naturalized section, the left and right in my previous diagram. And importantly, these are cumulative water balance quantities. So you look at precipitation, it's the blue line, it's monotonic increasing. It's the total amount of precipitation that's fallen on that test section over the monitoring period, over the 14 years that I show in this particular graph. So there's a couple of things you see here. You know, early on, the percolation rates are pretty low. That's what we wanted, right? But you see there's also some of these episodic changes, very small but subtle changes in slope. And then after several years of exposure in the field, the percolation rate changes. It changes really substantially here in the conventional one. And we go from a few millimeters a year to 10 to 50 millimeters per year, really very large percolation rates. We see at the same time when that percolation is climbing, that the precipitation lines and the evapotranspiration lines begin to deviate. What that's saying is no longer is essentially all the water falling onto that system essentially being stored and then sent back to the atmosphere. But the barrier layer at depth is now allowing that water to escape and flow through and no longer available for evapotranspiration. So you see the two lines are deviating, indicating that that water that reached the surface is lost. Now, a little bit of that is lateral flow, but nearly all of that is percolation. The barrier changed several years after it had been in service. Not 100 years, not 500 years, but several years. The percolation rate's much higher than anybody would have anticipated. Now that's the conventional side. The naturalized side showed some of those changes earlier. Similar graph here on the right. This is the test section that was on the right-hand side of my aerial drawing that I showed earlier. At this test section, it was only 2 or 3 years when we began to see these spikes of percolation coming through at a much greater rate. And then around 2014, like the conventional, it really began to exhibit a high rate of percolation. And we saw that same deviation of precipitation and evapotranspiration occurring. So these systems meant to function in a certain way for 1,000 years are changing in less than a decade. In fact, in about 5 years, their performance has been altered substantially. Now, we operated these, as I mentioned, for 7 years as just duplicates, maintained them, operated them just like we would a conventional melt tailings disposal facility. And then in 2015, we stopped spraying the herbicide on the naturalized section. We stopped maintaining it. We just watched it. And we can see when we look at our water balance data that, wow, things have changed. The percolation rate on the conventional section continues to climb. It's just really high percolation rate. We see that within a year or so after stopping to spray the herbicide, the percolation rate ceases. We have one little blip here that corresponds to a snowmelt event, but outside of that, virtually none. Very low percolation rate. Contrast that again to the conventional with very high percolation rates throughout the record. What's going on there? Well, we stopped managing it. We stopped spraying it. We stopped fighting nature, and we allowed nature to begin to inhabit the test section, the naturalized test section. This is what we see. Early on, we saw evolution of grasses, forbs, and then within a few years, development of shrubs. And these are huge water harvesters, rabbit brush, sagebrush, that type of woody vegetation extends roots down into the system, harvests that water and sends it back to the atmosphere. And over time, that surface has become similar to what we see in the surrounding environment, which is a shrub steppe environment. And we demonstrated that by doing vegetative surveys that we show here on the left. But the point is the vegetation came in. How did that affect the percolation rates? Well, let's look at the data again. Here's annual percolation versus time. And we're seeing up through 2015, our precipitation in blue, and particularly our conventional section and our naturalized section in green, conventional gray and naturalized in green. You can see the percolation rates are climbing. And particularly here towards as we reach 2015, we had over 40 millimeters of percolation in 1 year from the conventional section. 1 year. Designed for 3 millimeters a year, and within 5-7 years, we're at over 40. Now we naturalize it. What happens? Well, as we naturalize it, we begin to pull water out by the emergence of vegetation. If we look at our naturalized section, while high early on, the percolation rates dropped off to de minimis amounts. And towards the end of the record, there's just really nothing coming through that naturalized section at all. Whereas our conventional section continues to have high percolation rates. In 1 year, almost 50 millimeters, where it was designed to be 3. And we can see when we look at the percolation rates from these two systems, the one on this right-hand graph, that's the percolation rate from the naturalized section. And on the x-axis, percolation rate from the conventional section. That over time, that naturalized section has considerably lower percolation rates. All the data over time are falling below the 1-to-1 line. In fact, later in the record, the data fall very far from the 1-to-1 line, indicating that we're getting much lower percolation rates from the naturalized test section. And we see that same thing too if we look at annual percolation versus water year precipitation. And particularly in the very wet years, which are the most challenging years, you can see our conventional versus our naturalized, both I show in brown pre-naturalization and green post-naturalization. We'll look primarily at the green dots. Notice how, for example, in 2016, same precipitation applied in both test sections, but our naturalized test section, just 1 year in to being naturalized, is considerably lower. And then we take another example much later on in 2019, again, almost 50 millimeters. And for the naturalized section, way down here, less than 10. So it's really changed its behavior substantially. Why did that happen? Well, these are pretty busy graphs, but I'm going to talk through them in a very expedient and simple way. The message is that the vegetation pulled out the moisture in that system that nature had placed from the surface. So we're getting precipitation, we're getting snow, we're getting snow melt, all that moisture is moving in down through our rock, into our protection layer, into our radon barrier. And if it moves in and that radon barrier has become more permeable, it escapes. The only way to remove it is to actually go back in and pull it out. And that's what the plant is doing with plant roots. You know, roots reach down in and pull that water and bring it out to the surface. And you can see the evidence of that when we look at these two different graphs. These show water contents as a function of time and different depths within the two different covers. But you can see on the left graph, this is conventional. We haven't altered this throughout the 15-year data record. And we can see, for example, the protection layer, it wets and dries each year, wets and dries, and it looks almost the same every year. The radon barrier, too, stays very wet throughout its entire record. It varies a little bit throughout the record, but not substantially. We did have a couple of periods around the time when things changed, when we did have some more desiccation, and that likely was the cause of this increase in percolation. Let's move over to our naturalized graph, and let's look at, particularly focus on this period after we began applying herbicide. What did we see? Water contents in the protective layer and in the radon barrier early on start to diminish slowly, but as the vegetation gets established, the roots are into the barrier layer and extracting that water and releasing it to the atmosphere. And you just see these water contents plummet because the vegetation is pulling that water out of the system. We're harnessing nature's capacity to manage that water to our benefit, to keep it out of the tailings below. Whereas our engineered system just was not able to do that because it was largely incongruent with its natural environment. Reasons for that, the changes in percolation, we saw an evolution of hydraulic conductivity. I won't go into this in detail, but we did tests on the radon barrier and the protection layer over time. And the saturated hydraulic conductivity of those barriers increased about a factor of at least 10, and is sometimes on the order of 500. And if we have increases in conductivity of that magnitude, we will have corresponding increases in percolation rate. Those barriers put in to be impermeable within 7 years became fairly permeable and were no longer effective. We did find that the protection layer was very good at providing thermal protection. Despite being out in an environment that's very seasonal with a hot summer and a cold winter, that we provided good thermal protection for the radon barrier throughout the duration of the experiment that we've conducted. Soil temperatures in the radon barrier always were above freezing. So these changes in percolation were due to other factors, not due to freeze thaw, but likely due to these subtle variations in water content in the radon barrier accumulating over years, subtle changes in volume due to those changes in water content, ultimately causing structure to develop and the hydraulic conductivity to increase. So what did we learn from this experiment? It's just some high-level lessons. One, all engineered barriers evolve over time, particularly ones where we don't have some way of protecting them permanently from degradation processes like freeze thaw, like wet dry. These don't have a geomembrane over the clay barrier. That clay barrier ultimately will wet and dry over time, and if it's not thermally protected, will freeze and thaw. They will become more permeable. They will transmit more percolation in the waste. We should recognize that and design around it. The armoring, even though it is effective for erosion control, really does nothing in terms of managing that degradation process. We found that allowing the armored covers to naturalize immediately improved their performance. Instead of fighting the natural condition around it, allow nature to inhabit that system, and the performance improved dramatically. So harnessing the capacity of nature to manage the water. We also found that those naturalized covers are more resilient. You may remember in some of the data, even those really wet years after we went through naturalization, percolation rates remained very, very low for the naturalized cover, whereas they were very, very high for the conventional cover. And perhaps an important factor, not so much from performance, but not only does it work better, it takes a lot less cost and effort to manage. So we can have a lower cost, better performing system by allowing it to essentially blend in with nature and stop maintaining it. So really important lessons learned. And now we're taking these principles and adopting them in Department of Energy facilities, new facilities that are being built, and historic facilities that we can renovate along these lines. So I'll stop here and take some questions. Krishna, I don't know if you want to do a transition here at all, but
Yeah, I think I will request all the participants to send the questions in the chat box to Professor Greg Benson. So you see him as a co-host, so you can send the messages directly to him. Did you receive some questions?
I'm looking in the chat. Yeah, there's Doug Diefenthal asked about what herbicide had been used. I don't have that handy, but I've got a report on it. I'll be glad to send that to you, a report and a manuscript on it. My colleague Jody Waugh, the ecologist, manages that side of the project, so I don't know. Amir, go ahead, Krishna.
Yeah, a few others sent questions to me. Instead of me, they should send directly to Professor Benson, because I cannot see, he cannot see my text messages, chat box.
Yeah, just put them in the chat.
Okay, I'll do that.
Yeah.
All right.
Yeah, whoever sent them, just put them in the chat. Somebody asked a question about, is it possible to consider the effect of temperature changes on the hydraulic conductivity for liners? Yes, there is, and the temperature effect tends to be modest. There's a couple of phenomena that occur. And one, we just have changes in viscosity of the pore water, which changes the hydrodynamic conditions, which change hydraulic conductivity. But also we get volume changes of the pores themselves, and that alters the conductivity. But just thermally driven changes without a change in state, for example, without freezing and thawing or drying, have really are modest effects on conductivity. We're talking things less than a factor of 2 generally. Another question. Somebody,
Craig,
John Bowders asked, was there any?
I have a question.
All right,
Can you hear
why don't
me?
you put it in the chat, Tunson? I can hear you, but why don't you put it in the chat, Tunson? I'm reading the ones in the chat. Okay?
All right.
Yeah. John Bowders had a question. Was there any difference between snowmelt versus rain? Great question, and a huge difference. In seasonal climates where we get snow accumulation on the surface, you imagine the rain accumulates as snowpack, and it may accumulate for a month or 2 months. And then in a matter of a week or so, completely melts and flows through the system. And so, yeah, very big difference between snowmelt events and precipitation events. And that's a big challenge for dealing, particularly for high elevation sites where you get large snowpacks. We've got a field site, southeast Idaho, where we get 3 meters of snowpack. Enormous challenges with managing the ingress of water during those snowmelt events. This is a good question from Doug again. Does vegetation absorb radioactivity or give off radon? Early on, one of the concerns about these facilities and the rationale for spreading them was concern about radionuclide uptake and transmission at the surface, as I mentioned early on. There was a complementary study to what we were doing to evaluate whether that really occurred or not in a substantive way. That was done by Jody Waugh, my colleague, and also by a group of students from the Navajo Nation in New Mexico. That study pretty convincingly showed that the uptake of radionuclides through vegetation and mill tailings covers was pretty modest, and that really did not pose an impact on the environment. So that pathway for radionuclide transport probably was overestimated early on. And so the idea of allowing the vegetation to develop on these systems to manage the water is favorable from a hydrologic point of view, and also not problematic from a radiological point of view. Good question, and one I meant to mention as I was speaking. So yeah, follow on what will happen to the animals that eat those grasses. Since the radionuclide uptake is very, very modest, the dose that they get is really negligible. Kristen Sample Lord asked about, what about maybe just stop applying herbicide at the very beginning rather than waiting 7 years like we did? And of course, we were doing an experiment with replicates at the beginning, but I think Kristen's point is an important one. And one of the recommendations of our study is to just stop applying herbicide. We don't need to be doing this. And in fact, what we really need to be thinking about is how can we naturalize this system even sooner, besides just stopping spraying, but are there other things that we can be doing, and really rethinking how that surface layer is constructed? Is a riprap layer alone the correct design, or should we be thinking of a riprap layer blended with fine textured materials that creates a more hospitable community for the plants, the vegetation to establish? And that's something actually we're hopefully going to be starting a field experiment on in the spring. A question asked if we had tailings below our bottom liner. In our facility, no, our test facility, but in the full-scale facility right in the background of my photographs, yes, there's 40 meters of tailings in that disposal facility. Question from Dave Daniels about, does the vegetation, ingress of vegetation affect essentially the radon control? And it certainly affects the hydraulic control, but interestingly enough, we did not find that we had substantial degradation in diffusive control of radon gas. That was part of our complementary study that we did for NRC and DOE that we completed last year, and there's a new reg document on that. So that it degrades the hydraulic function substantially, but the gaseous diffusion function is not altered in nearly a significant way. The diffusion coefficients do increase, the radon fluxes do increase, but they don't increase in as substantial a way as we see the hydraulic fluxes. And what was interesting in the historic sites that we've evaluated, even though they've been in service for 30 years, all of them, even though their radon fluxes increased to some extent, still met the compliance requirements for radon emission rates. That was a really favorable finding. Joe Scalia asked about the native vegetation to be dominated by bryophytes. Is there a concern about pulling out moisture and contaminants that man places in the disposal facility? A question that we brought about earlier. And we found, again, as I mentioned, that radionuclide uptake and other contaminants has not been a substantial issue. It's much less of an issue than thought going on when this type of cover design was developed. Let's see. I'm just scanning through these questions. Does the effectiveness of vegetative cover change what is considered an acceptable environment for mill tailing storage? That's a really good question. And you might think, the sites that we're talking about are sites in the Western US, which are semi-arid. And we have the capacity in that environment to manage the hydrology naturally. If we go to the Eastern United States, we're hydrologically very different, much more water to manage. This process would not be nearly as effective because we have much more water than the ecosystem can manage internally and return to the atmosphere through plant transpiration. In the East Coast, something like this would not work. So the environment is important, and these findings really apply to sites in the Western United States or in other countries in more semi-arid areas. In the United States, most of these sites are in the West, although they're not all in the West. Another question is about adding, can you add specific types of vegetation to enhance performance? We haven't found that essentially customizing the vegetation is very effective or practical. There have been some studies done where investigators have tried to essentially put in certain species that were, for example, great water harvesters. And what we found is that, nature looks at that and says, you put that in today, and in 10 years, you will have a vegetative community that looks like the surroundings, because that's the equilibrium that exists in that particular environment. And we found this in repeated field tests that put in a custom vegetation. Within 10 years, the local vegetative community that exists in the surrounding area will invade and take over that cover system. And the species that were placed in the context of a custom vegetation are non-existent. I find from a cover design perspective, coming to visit a site, one of the things I do is I always look at the surrounding ecosystem. What is nature doing to manage the water in that system, to manage degradation of that system over time? How is nature doing that? How can I emulate that as an engineer? I think I got one or two more questions. So I still have a few more minutes. Krishna, is that okay?
Yeah. Just I think let's take one or two questions and then.
Yeah. Okay.
So you have a lot of questions.
Yeah, I have one from Tansu. Yeah, a lot of these are great questions. Tansu asked, for a radioactive disposal site where you need protection for many years, what do you suggest for management? Is there an effective service life after which the cover needs to be replaced? And it's a great question. And the philosophy, at least in the radioactive waste world, is to design a system that we will manage for 100 years, often called the institutional control period, and then we walk away from it. And it then needs to last at least another 900 years. And for some sites that I'm working on right now, up to 10,000 years that, without maintenance, without reconstruction. And the thinking there, that forces the designer to really recalibrate how they go about design, because they don't need to think about making something last for a few decades or a century, but they have to make it last essentially in perpetuity. And really requires the scientist and the engineer to think deeply about the assumptions they make and whether they're consistent with the observations that we see in the surrounding natural world. Now, I'm not saying that we can do all that and necessarily know it's going to work for 1,000 years or 10,000 years, but just the demand as that is a design goal forces us to think about these problems much more deeply and approach the design and construction process with a whole nother level of rigor than we do for any other type of disposal facility. I would say that the one thing that we're doing that perhaps is most important to achieve that goal of something that essentially lasts forever is to study what we see in the natural environment. What do we see in natural geological environments and natural ecological environments in the regions where we're creating disposal facilities? Those are the ecologically consistent equilibrium environments that can persist forever. See how nature has engineered those systems, which have lasted for centuries or millennia, and figure out how we can use the characteristics of those and embed them into our design. We call that a natural analog design, and that's really where a lot of this is going today, to create a design that essentially will last in perpetuity without having to be replaced or managed. That's a big challenge. And I don't think I'll be around to see how it turns out in 1,000 years. I'll have less gray hair than I do today. I'll have less hair altogether. I think that's probably the last one.
Yeah, thanks, Greg. I mean, if you can stop sharing the video, maybe some of our friends wants to say hello to you. So maybe they can show the video and say hello to Professor Craig Benson. The one thing I want to ask Craig, we have a lot of young researchers joining this webinar. I know based on your presentation, you show how important it is to do the field research, right? Field scale testing, and also having the patients to put the instrumentation and collect the data for a long period of time. And, that will really help understand the performance and all the fundamentals. So can you advise our young researchers on this issue?
Well, as an engineer, and as an academic engineer, it's not about doing projects and writing papers. It's about creating knowledge that people can use, particularly people in industry. And if we want people to actually take our ideas and implement them in practice, we need to reach into their world and understand their problems. And part of that's about actually proving that we can take our intellectual ideas that we may have in the laboratory and our computer model, actually realize them in the field. I've been running field experiments since my first one in 1991 that I built when I was still in my 20s until today. And I found the ability to engage in field research, couple it with laboratory work and simulation, brings it all together and allows you to understand how real systems function and actually how they can be translated into practice. The things that came out of our Acap program and this particular program we've been doing for DOE, EM, and LM, people use it. They're actually implementing the things that we've learned from these field studies because they've seen it work in action. We have the Monticello disposal facility I mentioned briefly. We have a test facility there with a 2.7 hectare lysimeter that we've been monitoring for 22 years. It is the largest, longest term field experiment conducted worldwide. And it's a treasure trove of information that's being used by Department of Energy as they develop and permit other sites throughout the West. So I would encourage anybody, any young person, if you have an opportunity to get involved in doing field work, it may take a little longer to get done. You have to be away from home. It's dirty, grungy work, but man, do you learn a lot. and it's a lot of fun. Thank you for that question, Krishna.
Yeah, thank you so much, Craig. So anybody has anything to say? Let's see. I'm not sure if the system allows anybody to show their video, but we had a really, yeah.
Hey, Joe.
I see Joe, I see Kristen. Thanks everyone to see. Yeah.
There's Tuncer. I see Tuncer on there.
Tuncer.
I'll be
Yep.
seeing Joe in a few weeks. He's got the Tailings and Mine Waste Conference coming up in Denver, right, Joe? Tuncer.
Joe. Yeah.
We got 15 minutes for our next meeting, Craig.
That's great.
He's a taskmaster, isn't he?
All right. Again, I want to thank Craig for taking his time and giving a wonderful webinar. I'm sure it is very useful for all the attendees. Thanks again, Craig, for taking time. Thanks everyone for attending. So see you all next Thursday.
Thank you, Krishna. Appreciate your leadership.
Yeah.
Thanks,
Bye.
Krishna. Thanks, Craig.
Bye, everyone.
Bye-bye.
Cheers, everybody.
Thanks.